Recently, astronomers have detected two deep space anomalies that simply shouldn't exist. Objects named ASCAP J1832-091 and GPM J1839-10. These are dead stars emitting synchronized bursts of X-rays and radio waves on a precise cycle second to generate enough power for their radio beams. These new anomalies spin far too slowly. Under our current understanding of physics, a star rotating at this pace lacks the internal energy to produce radio signals at all. They should be dark. Since their own rotation cannot account for these energetic pulses, these stars must be drawing power from an invisible external source. To explain these pulses, astronomers have moved past the model of a solitary, isolated star. Instead, the evidence suggests these objects are the central components of a naturally occurring electrical circuit. These systems function as cosmic batteries. They rely on the same physical laws that power an electrical generator on Earth. This discovery indicates that magnetic fields can create direct electrical links across millions of miles of empty space, allowing these systems to generate and channel electromagnetic power far beyond the capacity of an individual star. In this cosmic generator, the rotor is a high-mass white dwarf, or a neutron star, spinning in the vacuum of space. This dead star generates an intense magnetic field that reaches out into the void like a web of invisible strings. The stator is a nearby companion, an M-dwarf star, or a planet, trapped within that magnetic web. As the companion orbits at high speeds, it physically plows through the magnetic strings. This is a subalfenic interaction. The movement acts like a dynamo, generating a current of millions of volts. This massive current of electrons is funneled directly down the magnetic strings, crashing into the dead star's poles. The energy is then released as the rhythmic radio waves detected by our telescopes. This creates a permanent, one-way electrical circuit that explains the clockwork timing of the radio pulses. This battery mechanic scales up from small stellar remnants to the most massive objects in the universe, astrophysical black holes. In a process called the cosmic battery, the intense radiation and rotation of a black hole's accretion disk generates an induction electric field. Over millions of years, this process stores magnetic energy until it reaches equipartition, the point where it can finally power the massive jets we see erupting from the centers of galaxies. From white dwarfs to supermassive black holes, the universe consistently uses these electromagnetic dynamos to manage and store extreme amounts of energy. To understand the sheer volume of power involved, we can look at the Crab pulsar. At the center of this nebula is a pulsar engine. That glowing blue region is synchrotron radiation, fueled by the central star injecting enough energy to drive the expansion of a debris cloud 6,500 light-years wide. There is a theoretical limit to this storage capacity, called the mass shedding limit. This is the exact rotational speed at which a star would physically break apart. A neutron star pushed to this edge holds a reservoir of 10 to the 53rd ergs. This makes it the most energy-dense object in the cosmos. Physicists are currently mapping out a theoretical framework to harness this power using quantum stellar batteries, or QSBs. Advanced civilizations could potentially use Dyson swarms and topological quantum matter to tap into the stellar energy, using the star as a stable, long-term power reservoir. However, Section 9 of the framework identifies a severe risk. If the circuit fails or the star collapses, the energy release is catastrophic. This uncontrolled discharge is the star bomb, an explosion resulting in superluminous supernovae or gamma-ray bursts that can devastate anything in their path. These dead stars function as self-regulating dynamos. They provide the universe with its most efficient method of storing energy, but they also possess the capacity for the universe's most violent electromagnetic outbursts.